so excited to be here. Today's session is on the future of robotics, and we're joined by two absolute geniuses. We have Kanishka Rao, who is the head of robotics at Google DeepMind, and Alberto Rodriguez, who's the head of robotics behavior at Boston Dynamics. So stoked to be with you guys.
It's great to be here.
Yeah, welcome to the stage.
Yeah.
I want to start us off by grounding this moment. As a kid, I always grew up loving robots. But it feels like 2026 is the year that a lot of it is actually coming to fruition. Can you kind of bring us up to speed on what's different this year and what breakthroughs have happened recently that has put us on this exponential?
I think, we're seeing so many breakthroughs in just like general purpose AI. We've seen just like in the last few days that the rate of progress in just like general AI in the digital world. And I think all these breakthroughs are making their way into the physical world and especially impacting how we do robotics. And if you think about for robots, if they have to be useful to us humans, they must understand our human world. And I think a lot of this understanding is coming from these like large frontier multimodal models. A few years ago, we took these large vision language models and then we adapted them for robotics by adding a third mode, which is like actions. So these are like physical tokens instead of your digital tokens. And it was kind of like mind-blowing to see the result of that, because all of a sudden you have this vision, language, and action model, and you could like talk to the robot, and you can ask it to do things, and you get all this like understanding for free in robotics. And I remember we put like a bunch of toys in front of the robot, and we asked the robot to pick up the extinct animal, and it like went for a dinosaur and picked up the dinosaur toy, and it was like an aha moment of like. Because again, the robot has never seen this in the training data. This was just like all kind of understanding coming from these digital, AI breakthroughs. So I think, robotics is really kind of riding this wave of just like general AI intelligence. And I think, we're kind of in a revolution in the robotics space as well.
We're also in an interesting moment where you guys are partnering. Can you tell me a little bit, Alberto, about that partnership and what you're working on? Because I think Boston Dynamics is like the robotics company. Like a lot of people have seen your robot videos, whether it be the robot dog 10 years ago. What are you working on now? How has that changed, and what's the partnership look like?
I would say that, okay, I'll be honest, like this is one question that I was prompted that we were going to get about the partnership, so I came a little bit prepared. And I was thinking, what problem I'm going to have on stage, and it's clear it's going to be a chair. So I spent reading a little bit of time how kids learn to sit. And you might relate to this. I think you have a 2-year-old.
I have a 2-year-old, yeah.
Yeah. So I was reading that there's clearly 2 stages in how kids learn to sit down. There's a first stage, which happens around 6 to 9 months old, when they learn the concept of balance, right? Like they sit on places and they know how to stay balanced upright with their head standing up. They learn the concept of how to stand up without falling forward or falling back, or without moving the chair back, for example. And then there's a second stage that happens when they are closer to 1.5-year-old, when they learn the notion of what's a chair, what's a place where you can sit, the affordance of sitting, right? And actually, it's funny, like there's a period of time where kids might just spend a few weeks just sitting on weird places, like on their toys or on a jacket on the floor, just to understand what it means to sit and what actually makes sense to sit. The idea that sitting has directionality, right? Like when you're sitting down, you're going to be facing a certain direction and no backwards. So if the chair were to be backwards, I should probably turn the chair so that I'm facing at you. And those 2 ideas relate to the 2 main ways in which we are building sort of generalization in robotics, right? There's physical intelligence, the idea that the robots we're building, they need to understand what it means to exert forces on the world, how to use their body to exert those forces. And then there's this idea of reasoning or common sense generalization. And like that they have to be able to interact with anything in the world, even if they haven't seen it before. That you can also sit right there on the ledge or on the table, and it's fine as long as you know how to balance. So there's 2 things that are interesting. One is that you cannot learn the second thing without first learning the first one. And like psychologists have like captured this like widely. But also the second thing is that we are building our robots with exactly the same model. We're building like 2 different sort of brains that are compatible with each other. And I would say that one of the cool things about this partnership is that we have sort of in combination a team that not just can provide like an excellent hardware, but also has the ability to bring those two things together. And it's kind of like the A team to build sort of a generalist robot for physical labor.
And historically, you guys were working on a lot of different form factors for robotics, but we're specifically talking about Atlas today.
Yeah.
Can you tell me about why a humanoid robot makes sense? Like, I feel like there are so many different morphologies that you could do for robots. How do you pick which one to use? I feel like we're moving from a world of like very specialized robotics, like robots in factories, like just an arm, to these more like generalist robots.
Mm-hmm. Yeah, I mean, we actually just released sort of the new generation of our Atlas robot, our humanoid robot at Boston Dynamics, which I believe in a second we'll be able to see a clip. But before just getting into your question, why humanoid, right? Why humanoids make sense? And I think that on one hand, maybe Kanishka can extend on this, like the promise of scaling up data collection as a means to create generalization and sort of common sense works best when you can learn from humans. That's sort of the seamless path to scale up data generation that feed these models. But also from a hardware perspective, actually the humanoid form factor, it turns out it also makes sense, right? Like having two arms is way, way better than just having one arm because you can balance loads more efficiently, because you can sort of reposition objects in a way that would be hard to do with just one arm. Having two legs, it turns out that allows you to get to almost any place that the humans can go. Not just because you can step up things, but you can also change your form factor, right? Like you can become thin in the right direction, but you can become strong to resist forces in the direction that you want. And being able to change that location of your feet also allows you to change the friction with the ground in a way that allows you to accelerate faster or decelerate faster more efficiently than you had wheels. So it just kind of makes sense.
Yeah, I think in robotics, we talk about physical AGI, and I think we define AGI in terms of like what us humans can do. So I think for physical AGI, I expect that the robot can do anything I can do, or an average human can do. So I think that just for that reason alone, like working or at least doing research on the humanoid is justified, because ultimately that will be the test of can the AGI do all the things, and the humanoid form factor is the best place to express that.
Sense. Let's look at the video.
Yeah, let's look at the video.
This is the new generation of Atlas.
Yes, this is the new generation of Atlas, and here you see doing it a very physical task, lifting a fridge and carrying it to one of our developers. This is very cool, sitting there. It just asked to bring a soda. I guess why we need a reasoning model to understand the difference between a soda and the fridge. But a couple of things that are very important about this robot and why it's very important for us and for the partnership. This robot, while it maintains sort of the physicality and agility that characterizes Boston Dynamics robots, it's been designed especially for mass manufacturing. So it has the simplicity in its design that is necessary to deliver on the reliability that we need to be able to do data collection at scale and deployments at scale. So we're like super happy that we've been able to combine those two things in the same piece of hardware.
Can we talk about data collection and kind of how we train robots? Because it seems like when I think about this AI moment that we're in, the breakthrough of the transformer has led to an exponentially huge amount of new information and better AI models, and it feels like with robotics, we've also experienced similar breakthroughs where historically we were training them by just like brute force, having them do the activity over and over and over again, and now there's this whole new level of training with training and simulation, but there's also still like teleoperation. Can you kind of break down for me the different ways we train robots and models? Yeah,
so in robotics right now, there's like maybe roughly like 2 ways to train robots, and things that you can simulate are easy to learn in simulation. So for example, the robot body itself, since you've built the hardware, or Boston Dynamics has built the hardware, you can build very good simulators for it. And Boston Dynamics, they're the state of the art at doing this. So if you can simulate the task, I think you can then train it. You have the same verifiable rewards loop, and you can like do RL, and you can train some really nice policies and simulation, and then you can transfer them to the real world, and that works well. So
that's how the fridge All the behavior was
exactly. So I
trained.
think a lot of like the walking, the running, the whole body, the dancing, all of this is powered through like really good simulation, and then setting up this RL loop in simulation. Then this other bucket of learning, which is maybe the harder bucket of learning, and this will take longer maybe. This is the kind of dexterity bucket where you cannot simulate the task because you want the robot to interact with all the objects in the world, and there's so many like different things and objects and the ways you manipulate them in the world. It's hard to simulate all of that. So on the manipulation side, what has really led to a lot of the latest advancements has been leveraging these large foundation models and then kind of weaving in real-world data with them. So I talked about VLAs a while ago. Essentially, what you try to do is you try to train the robot on real-world data, and you have these physical tokens collected through teleoperation, and we kind of interleave them with like vision and language tokens, and that is a way to kind of generalize the dexterity a bit more. But yeah, that bucket is mostly relying on real-world data collect.
And what is teleoperation? Like, how does that actually work? What is teleoperation?
Teleoperation is essentially, so the way the robots learn about the physical world is just like we do. It's through your own embodied experience. It's not showing a video to a robot and then it kind of learns that. Maybe in a year or so we'll be there. But at least for today, it's really important to understand how the robot moves. The robot needs to understand, hey, if I poke my finger right now, like what will the world do? So teleoperation is how when we collect data, we control the robot to move in the world and to do the task. And that way it builds this like physics knowledge by interaction. So it's a human controlling a robot and then the robot doing the task. And through this teleoperation data, it kind of learns physics and the task. And that's been the state-of-the-art way of doing manipulation today. And
I would say that the tighter the embodiment of the pilot that is teleoperating the robot, the better the data that it can generate, right? Like in practice, what happens is that we usually put pilots in VR headsets so that they can actually see through the eyes of the robot so that they don't get to use information that the robot would not have when it would try to do the exact same task. So that this notion of what the robot will be able to observe is like ideally replicated one-to-one with what the pilots or demonstrators are generating.
What are the phases of this? Like, do we need more different types of training data to really get robots in the real world, or is like visual training data enough and we just need a lot more of it?
I think we can still do more with teleoperation, just because I think we haven't really found like we've seen a lot of generality, but we still haven't found like that basic recipe of like, again, if you think about like vision, language, action models, there's way more vision and language tokens than action tokens.
Okay.
So I think the strategy for robotics right now is how do you leverage the intelligence in these bigger things to then accelerate robotics. So just last year we announced our Gemini robotics model. And there, one of the breakthroughs that we showed was we can kind of introduce thinking in the physical world. So the idea there is, typically in the digital world, when you think, it's mostly about like what code you're going to write or what text you're going to output. With this model, we had thinking about your physical actions. So it would be like, if you're trying to grab like something, it would be something like, should I close my hand right now? Will it pick up the object, or should I move further and then close my hand? So by interleaving this thinking with physical, action tokens, we're trying to make the actions a bit more general. So we're getting more kind of bang for our buck in terms of like the data. And I think we have a video of this in like a laundry sorting video. Maybe you can take a look at that.
Yeah, let's do it.
Now with thinking, we're able to ask the robot to like chain a whole series of tasks together, and it's completely end-to-end. The thoughts and the actions are interleaved. I can see it running in person, which is really cool. Let's see what it does with the white cloth here. It's still trying to go for, okay, so here it's seeing, it said adjust the black bin a little bit so I can pick up the cloth. So this is really cool. We didn't really train it to do this explicit thing. So these kind of thoughts just like emerges during inference, which is really cool to see. And it's super reactive. I can now switch this up on it, sorry, Apollo. And it knows that I have done that and it will react. So I think this is what we mean by generalization for robotics, because you can train a robot to be pretty instinctive and do repetitive things, but what makes us humans so good at all of this is when faced with a new situation, we can kind of think our way through and solve that new thing. So this was an example where this setup was not in the training data, but it could like think its way out of that problem. Yeah.
Okay, yeah, like I see a video like that, I'm like, this is extraordinary. Like the robot's like in real time, it feels like a huge breakthrough. Which leads me to this bigger question that I feel like a lot of people in the room have probably experienced seeing like hundreds of robots dancing in sync on Twitter, but then a video like that or a video of a robot picking up a banana is actually like the more impressive one. How can people understand the videos online of robots and like what's a genuine breakthrough versus like what's been like pre-programmed that is impressive but like less impressive?
Yeah, so I think as you said earlier, I think the manipulation part of the problem is probably going to be, I think the final chapter in robotics is like, that's the most difficult part. And sometimes I work.
It's probably the only chapter, right? Like getting robots to dance, is, you know, it only gets you this far. But
exactly. So yeah, I feel like
not many people are going to pay for that.
Yeah, we work with this stuff every day, but it's hard to express to everybody how difficult like dexterity is. We have these amazing hands that we use all the time, and we take it for granted. Like, but it is really hard. Like if you look at the state of AI today, we can code up operating systems in like whatever 24 hours, and we can solve complicated math, but we can't scramble eggs. Like that.
Yeah, why is that hard?
Yeah, it is because this physical intelligence it feels slightly different than the digital intelligence. Like again, I have a 2-year-old at home, and he can walk and run and climb. He's even can do some speech recognition and talking and language understanding, but he still struggles with dexterity. Like I don't think he can open up this can of water or like zippers. So there's something different about physical intelligence, and I think our researcher of robotics will tell us about ourselves too. Like how do we learn this stuff and why is it different? But yeah, the one thing I would say is like the dexterity stuff, as Alberto also said, is like the more difficult part of robotics versus like the dancing and the walking and the running, just because, we still haven't cracked that problem fully yet.
Yeah, I would say that like even just from a technology perspective of what's available to us today, like there's two, as you were explaining, there's two techniques that we mostly use to engineer behaviors or to get generality to emerge, which is one, learning from demonstration, and two, learning from trial and error, mostly in simulation, because that's the only place where we can sort of do the very expensive search of trial and error. And doing something like just grabbing this bottle and opening this cap is something that it is, one, very difficult to demonstrate. If you imagine putting yourself in the mindset of a pilot that is piloting the robot, being able to do this without feeling the forces that you are feeling as you're trying to screw or unscrew the cup is just very difficult. But it's also very difficult to simulate realistically the compression that happens in the skin and the sensing that happens in the sensors in the fingertips in my hand to understand what's the behavior that is going to drive this. So we have ideas for how to solve those problems reliably, but we still don't have sort of the one key technique that is going to enable the kind of dexterity that we want at the reliability level that is necessary for like industrial scale deployments that actually have value.
Would we have to create like almost like a haptic model where it's like giving, like I think right now most of our breakthroughs have been the robots like just seeing things through cameras. How do we make them like feel things? Like is there a new type of model that comes out?
So so I think the tactile puzzle it's a real puzzle, and I think today all the state-of-the-art models that we are showing, at least for manipulation, they are vision-based, which is again is a bit weird because if you think about all the manipulation that you're doing today in your daily lives, you're probably using your like sense of touch and haptics way more than vision. So it's a bit of a conundrum, but maybe there's a few reasons for why vision is like state-of-the-art today. I think one is again we're building these models on top of frontier models. And there's way more vision data on the internet than any tactile data. Really? So I think just like the size of the data set. I think the other thing is we do use these like wrist cameras. So for robotics, you might see sometimes there's a camera on the wrist or the end effector, and that gives you like a close-up view of like the actual contact points. So maybe instead of actually feeling these things, if like in the pixels you can capture the compression as you were talking about, maybe that's a substitute for tactile in the meantime, and that's kind of how it's working. So there's some like unreasonable effectiveness of this vision stuff. And I think we have a clip of, maybe we can show this now, of like a dexterity task that we did.
Like origami, right?
Yeah, so we're using the robot to like fold origami. And this model is completely vision-based. There's no sense of touch or force or any of that. And if you think about it, this task should have not been possible just by vision, but it is able to learn this quite effectively. And again, it's like looking at the creases, the folds, and it's probably inferring the forces and the sense of touch from this. So it's kind of neat that this is working with just vision. But I do feel that ultimately, yeah, I think hardware will get better.
Yep.
I think one thing is like cameras are like so ubiquitous. The skin is hard to hardware.
Yeah.
So I think those maybe hardware developments will like also lead to some of this research. But yeah, as of today, vision is like what's helping us get through this.
Yeah, maybe just an anecdote of like how important tactile is, right? So part of the process of scaling data collection at the very, very large scale is equipping people with wearables, like putting like a camera on your forehead and just asking people to just go by their lives, just doing as if they were doing normal life, and then using that as a means for pre-training the very large-scale models that sort of reason about behavior. But it turns out that if you do that, the way that people move through their lives is like this. They're doing something here, and while they're thinking about what's the next thing they're going to do, they do it here, and then they move. So actually, the cameras, their eyes are not looking at what they do with their hands. Turns out that most of what people do is driven by tactile feedback and proprioception, and they don't need to look at it other than just for a fraction of a second to understand what to do and then how to lock in the hands and then just let the hands do their magic. So my hypothesis, my bet is that we're not there yet because we're limited by hardware reliability when it comes to tactile sensing and cutaneous sensing. But the moment we get there, and I'm pretty sure we will get there because there's like tons of interest today, we are probably going to see a gradual transition to relying less for control loops, or for high-frequency control loops on visual sensing, and using it more for like common sense understanding, and using more tactile sensations for driving manipulation.
Yeah, I saw a really interesting study where this doctor numbed patients' hands and then watched how well they were able to do different tasks. And it was pretty atrocious. Like, people were not able to do much. So it's amazing to me that it was, the robot was able to learn any level of origami. I'm curious, when we think about like the different stages of robots, it seems like we have a lot of robots in factories right now, and then maybe like the second level is like front of house, and then the third level is like homes. What's the roadmap look like? Like, when do you think people in this room will have like a robot in their life, and what breakthroughs are kind of on our journey to get there?
So yeah, it definitely will be a while. It's not next year. So yeah, sorry.
What?
Things you hate to hear.
So yeah, I think maybe like the next 5 to 10 years we'll start seeing.
Good.
Yeah, I think again like the main. If there's one takeaway of this, I would say is like dexterity is hard and it's still an unsolved problem. So I think that's like one of the main challenges that we still have to solve. I think even generality is not fully solved. Like maybe we can learn to open like this bottle, but the robot still struggles to open like any bottle. Like this, when humans learn a skill of like unscrewing something, we can start unscrewing like almost anything. Like so we can reapply these like verbs to like most things. But robots kind of like are still a bit narrow-minded. They can learn a verb with like a few objects, and then maybe it'll generalize to a few more, but they don't like universally learn that skill. So I think generality is still like a big bottleneck, and then dexterity is like probably the big one that we still have to solve. And I think as Alberto said, like maybe we still are waiting for some hardware breakthroughs. Like a simple task, like again, like for dexterity is like picking out keys out of your pocket or like a purse. Like that's like so difficult for a robot to do. Like we won't even attempt that today, but it's something we just naturally do every day. So I think there's still ways to go where hardware has to like meet us there for like tactile sensations. So there's still like work to be done.
What are robots really good at today? Like if we were to like create like a list of like what they're already excelling at and exceptional, what would it be?
So I think again, like we have seen, they're very good at whole body control. So even like a few years ago, like humanoids would not been a thing because balancing was so hard. But again, like with really good simulation and state-of-the-art, breakthroughs in reinforcement learning, kind of balancing is solved. I would say. I don't know if that's a hot take anymore, but balancing is solved. So like humanoids are more
problem.
Okay, you agree? Okay, so humanoids are more possible now. We can see them walking around, and I think like basic manipulation of like picking up something and placing it somewhere else. They're quite good at imitation learning. Plus, this human collected data is working well. So I think basic pick and place and walking, and obviously like the dancing and all of this today, yeah, they're very good at.
Yeah, if you look at industrial tasks, for example, in manufacturing,
Yeah.
the leading skills that are necessary to make an impact are things that are actually very complex, right? So it's like handling cables, right? So you want to be able to handle something that is very deformable and put it somewhere routed through hooks. It's using power tools, right? So you want to be able to grab a bolt driver, like feel the strength of a good grasp, which is something that actually takes many years for people to know, right? Or just imagine a screwdriver. How long does it take for someone to actually feel what it feels to hold a screwdriver like in a way that you will feel confident to actually use it? Some people never actually learn how to do that. So using power tools. And then the third one is bin picking, right? So there's a bin full of objects and you want to fish one, not two, or not three, or not zero, but just one. Even the ones that get stuck in the corner of the bin. Those are like very hard things to do still today. But I think that we are on a great trajectory from sort of trying to squeeze and continue to invest in this bet that learning from demonstration, just like we've seen with large language models, has like a very long route to saturate performance. I'm convinced that performance will saturate just from demonstration. At some point, robots are going to have to continue to improve performance from trial and error. They're going to have to get there, make mistakes, recognize, feel what it feels to fail at something, and learn from that. Just like RL is sort of like extremely impactful in bringing large language models to high performance.
Yeah.
The same thing is going to happen in robotics.
Is there a robotic equivalent to like muscle memory, like how a human that's like played piano 1,000 times is able to play and not really think about it? Like, are there tasks that the robot just gets so good at that it kind of runs at a lower level?
So I would say most robot models today are in the regime of muscle memory because again they see the state and they just kind of react. There's no thinking involved except for the latest models that we're working on. So I think they're kind of moving away from the muscle memory reactive mode to more like thinking a bit more about what they're doing and in the more thinking intelligent mode. However, it's reactive, but it's still like a large vision model that's controlling this. So in that sense, it's not tactile based, but it's kind of a vision based reactive model that it just sees an image and it kind of like makes a move, and it doesn't really think about why it's making that move. Like if you ask even the state of the art robotics models today, hey, why did you take that action? They don't give you an answer. So
interesting.
Yeah, they don't. Yeah, so it's more of like a reactive thing where the actions are just like outputted, but they cannot explain to you why they did that.
How does the new model change that?
So yeah, the new models, basically what we did is we kind of interleaved thinking tokens and then action tokens. So before it outputs an action, we basically explicitly added some tokens about like what it was doing, and this thinking could influence why it was taking the actions. So it still doesn't explain why it took the action, but at least you can see the thought trace that led to that action.
Okay.
And if you tweak the thought process, you actually get different actions. So you can kind of influence the action this way. So again, it's a little bit trying to connect that intelligence of like motion and physicality to like the digital intelligence, but it's still not fully there yet where you can just talk to the robot, hey, why did you do that? Can
you give me an example of like something that you would tweak that would then lead to a different action?
It's just simple things like it's like let's say it's trying to grab something and its thought processes that it might say, hey, I'm close enough to close my hand and I will grab the water bottle, and if that's its thinking trace, it will just close its hand. But the experiments we try to do is we edit the thinking trace and we say, I'm not close enough, I need to go lower, and if that's the thought it's conditioned on, then the action would be to go lower. So you can kind of like, it makes the models more interpretable and also kind of steerable because you can like, look at the thoughts and understand like why is it taking that action.
And is it that would replace like the VLAs, does that replace the other types of models, or is it they all kind of come together?
So at least this model I talked about was still like a VLA style model where it's like, it's based on top of a vision language model. I think the one interesting thing is, we're talking about how robotics is getting impacted by like these big breakthroughs in like
Yeah.
just large frontier models. And I think the one thing I'm really excited about is we saw these omni models and
Let's
video
go,
models.
yes.
And again, like we're talking about physical intelligence, which is intelligence about like motion and like physics and gravity and like friction and all these things. And these are not really captured in language or even an image. But these models, the video models, these world models, they are able to output videos that look pretty
Yes.
realistic, right? And I've played around with them and tried to ask them to create videos of like dexterous, manipulation, and they look pretty good. So they do seem to, again, yeah, Demos was talking about how they understand some basic physics. I do think that they have some understanding of physics through video prediction, and it will be really interesting to see how, again, robotics can leverage some of this like physics and motion intelligence, and then build kind of robot models on top of that.
At Boston Dynamics, what are you personally spending your most time on right now?
Sorry, what?
At Boston Dynamics, what are you personally spending the most amount of time on right now?
The most interesting thing we're working on right now?
Or what are you like spending the most amount of time on?
Oh, the most amount of time. Yeah.
Yeah.
So for us, we design robots not because we like designing robots, but because we know that there's certain sort of physicality that is possible to generate through motion, and we want to bring that to products for our customers. And one of the things that we're most interested in is sort of understanding what's the right kind of balance of models to be able to our robots develop a sense of general physical understanding of interacting with the world. Right? There's some sense of frequency analysis, so to speak, in how a robot has to make decisions that tells us already that there's certain things that have to be decided like once per second, like when you decide, oh, this is the thing that I want to interact with, and it's not that thing, and I should reach out with a certain sort of direction or with a certain sort of pre-shape of the hand. But then there's certain decisions that have to be done way, way, way faster, because when the hand sort of is accommodating to the bottle, it's a control loop that the robot has to make decisions, 50 times a second or 100 times a second. The same thing happens with balance, right? When the robot is trying to carry the fridge, and it needs to react to the fridge sort of like side balancing. And sort of the fact that there's these like differences in frequency in which the robot has to make decisions already tell us that we need sort of an architecture that it is tailored to that sort of decision making. So we're very interested in understanding what is the right structure to drive a system that has general physical understanding, and what's the right way to populate it with intelligence, right? Is it just demonstration, or is it trial and error, or a combination of those two things?
Totally. So on my channel, I make optimistic tech videos, like what the future will look like if things go well. And I think you guys are two of the driving forces in making that future amazing. I want to hear from both of you. Take me into your head. Like, what does your vision for the future look like? What are you trying to get us to? Like, if everything goes right, what does the world look like in 10 years from now?
Great question. Yeah, so I think...
How many millions of humanoids are we going to have 10 years from now?
Yeah, I think if everything goes well and we can solve like dexterity, I think there's still like a huge like safety research puzzle as well. I think robots are not going to be useful unless they can be really safe. Yep. So I think that's another big roadblock. I think in that sense, robotics is kind of like autonomous driving too. Like we have to really solve that part too. It can't be like a side thought. So we're developing, all our safety AIs along with this. But I think, in 10 years, okay, if we are successful, I do think like a lot of kind of basic general day-to-day stuff we can have robots do, and I think we'll see robots more kind of amongst us, helping us. I just on a personal note, I hate to do like daily chores, and like I know it's a very first world problem, but I think a lot of those kinds of things, the boring, the dull, the repetitive, the dangerous tasks. Robots will be, physically doing, and I think, generally, the goal is to benefit humanity, and I think, physical intelligence can enable all these form factors to help us in that. So that's the dream. Yeah, in 10 years that we will be there.
I think you guys can do it.
Yeah.
What about for you?
Yeah, I would say similar. Like the thing that drives us is to make like arduous physical labor, the kind of that is like backbreaking and very tedious, an option, right? And we're doing it with our existing products, like Stretch is a robot that unloads boxes from trucks. And these boxes are like 50 to 60 pounds. And these trucks, they're not controlled for temperature. So sometimes they can be at 100 Fahrenheit, right? And the robot does it, and it doesn't complain. Or Spot is another example, right? Where you will deploy to patrol and do inspections in your factory every day at the exact same time of the day and do inspections on the same 100 places in your factory or 1,000 inspection points. And it has to do that every single day. And most of those days, maybe 499 times in a row, nothing will happen. Extremely tedious. But then all of a sudden, the 500th time, something feels off, right, in one of the pieces of machinery in your factory. And having to keep the attention span and having to keep the interest in sort of understanding that just something went wrong is very, very tedious. And using robots to do those kinds of jobs, it kind of makes sense. And we want Atlas, we're targeting Atlas as a machine that is capable of very arduous labor, right? That's why it's strong, that's why it has the kind of payload that it has.
So you're more focused on like the industrial side of robotics, would you say?
At the time, currently, yes. Clearly, we've sort of seen that industry, especially manufacturing, is a good entry point, at least for us. It gives us a window into a market that has the right cost for where humanoids are today. And it gives us a window where there are ways to like mitigate safety concerns in ways that would be very difficult to do at home, for example.
Yeah.
And sort of gives us a ramp up to eventually go to other markets that, like home, for example, that could also be extremely beneficial.
All right, well, that's amazing. I admire both of you so much. Thank you for the panel. Thanks everyone for watching.